Yeah. It depends on the weight you ascribe to the different objectives. And that is for the decision maker. And often the decision maker is not the design engineer who produces this curve. So if it's very little, indeed if it's very little, you might consider that actually B is better because you haven't really made the other worse. So the question is, do you consider them to be both on the Pareto front or actually non-different in one objective and a lot better in the other? So again, this brings us to the next point, which is how do you solve multi-objective optimization solution methods? How do you solve them? There's a number of methods. I'm going to talk only about the simplest one, which is not always guaranteed to give you the Pareto front, but let's look at it. We're going to call it scalarization. Basically, you take all the objectives and somehow you merge them, you aggregate them into one single objective. So you assign different weights to different objectives, you combine them into a cumulative one, and it is a subjective method because the weights are based on experience of relative importance of objectives. But you still can use them to generate parts of the Pareto front and then make your decision based on that. So basically what you do, instead of saying minimize the whole vector of the objectives, I just sum up my objectives Fi weighted by a scalar omega I for each objective, where the sum of the omega is equal to 1 and omega are between 0 and 1. So it's a scalar weight of measuring the contribution of each objective to the aggregate objective. Yes?
So this is what a carbon tax is supposed to do, in a way, because if you wanted to maximize your profits while minimizing the amount of carbon that you use, that would be the two objective function. But if you simply put a money cost on the production of the use of some amount of carbon, does this weighting of the two together and rolls them into one variable, which is your profit after you've adjusted for paying the carbon tax.
Yeah.
That's the only way I can understand it.
Yeah. And also, if you want to think of this is interesting that you said it. Is this dimensionless omega? F may have units. And that's what I'm always telling people and my students. Think as engineers when you look at quantities. They have units. You're adding them together. Are omega I dimensionless? They can't be really. You're reducing them to some common kind of currency, if you like, so that you can add them together. A typical thing you can do is to convert somehow your objectives in monetary terms. Everything is measured in money. So that's...
So this is all figures of merit should be per dollar. And the main thing I learned in material science.
Yeah. So this is the scalarization method. What can it do? Well, what it does is the following. Remember, let me go back. My variable space is x. I'm choosing x. I plug it in here, and I try to minimize this. So this is what you're doing. This is my feasible values of x, which satisfy the constraints. I plug them into the objective, and with appropriate weighting, I can start minimizing the aggregate function, and this will be the result of the minimization. But the whole blue space is the set of all objective functions that correspond to all feasible values of x. And the minimization, the Pareto front, is just the lower part of this space of objective functions. Is that clear what's happening? So If I don't minimize, pick a value from here, map it here, it's going to map somewhere in the blue. If you minimize, depending on the different weightings you use, you're going to land on the lower part of this set. And so by changing omegas, for example, you're sliding up and down the Pareto front. Not always, because if you have a non-convex Pareto curve front, the scalarization method is not going to be able to give you the part between 3 and 4, because it's not convex. But it will generate all the others. And then what you do is, let me go back a few steps. Once you generate a front like this, could be 3-dimensional as well, if you have 3 objectives, you present this to a decision maker. And you say, if you want to achieve this much cost in the process, then the risk of the process is this. Is this an acceptable scenario? No, I want lower risk. You want lower risk, it means you achieve higher cost. You're forced to do higher cost. So it balances the trade-offs. One more, and we break for Friday. The next type of optimization problem. So far I've presented to you 2 types of optimization problems, optimal control problems and multi-objective optimization, but that is not to say that an optimal control problem cannot be within a multi-objective optimization task. It's just that I want to isolate different types of formulations, and then there will be combinations where one fits into the other, and you could build a hierarchy of such types of models depending on what you're solving. And this is beginning to show this sense of hierarchy where we have one optimization problem inside the other. Could be of any nature. So a bilevel programming problem contains a subset of the variables which is required to be an optimal solution of a second optimization problem. Or in other words, one optimization problem is constrained by another optimization problem. And the best thing always to do is to motivate it by an example before I show you an abstract formulation. Let's consider that we want to predict how to genetically modify a yeast or a bacterium in order for it to overproduce a product we're interested in. It could be a bacterium which is producing an enzyme that we're interested in to sell, and we want to make it overproduce than what it's already producing in its native strain. So we want to modify a biochemical reaction pathway to achieve improved productivity of a metabolite using model-based techniques to propose alternative genes to knock out. One could argue to also enhance by adding more copies of the gene, but we won't get into that. Why you want to do that? Because obviously, if you're going to do this by experimental ways, either combinatorial experiments or by experience, you're going to run a lot of trials which have a lot of cost as well as a lot of time invested in them. Now, if we had kinetics for all the reactions in metabolic pathways, we could measure the sensitivity of process output to given enzyme concentrations, knock out the genes that code for metabolites that inhibit reactions on the productive pathway, consume metabolic products needed in the productive pathway, and sort of try to restrict the side reactions so that you enhance the path that leads you to the product. For accuracy of such a modeling approach, we would also need to know genome control mechanisms, operands, on the metabolic reactions. And that would be a horrendously nonlinear and complex model for which you would not even dream of being able to measure the parameters required for it. So, as such, we can view the reactions to be ordinary chemical reaction pathways, and we need some special handling to predict reliable modifications. So the idea is the following. Use fluxes or rates of reactions through metabolic pathways by using the stoichiometry of reactions involved without kinetics, so it's like pseudo-steady state. Find native states of the fluxes by measuring some rates and predict redistribution of subjects of fluxes subject to gene knockout. And the redistribution prediction is the key here. The fluxes will redistribute according to what criterion? And this is a reference here in the work of Maranas and others. OPNOC is a famous approach they used. So I went back. And here is the general idea. Let's start from the inside of this model. You have the pathway, and if you have a full genome, you know every reaction that takes place, you know the stoichiometries, you know the reactants, you just don't know kinetics. So you have an incomplete model. You can try to complete it in order to have unique values for all the reaction rates by assuming that these linear constraints, stoichiometric constraints are linear, are the constraints which belong to an optimization problem that the organism is trying to solve for itself. Okay, so basically you have a system of rates at steady state. You have fewer equations than variables. You can't proceed with this, but you could proceed. Well, you have bounds also. If you assume that the organism itself is trying to maximize a linear, let's say, objective. What this will do, it will create artificial, perhaps, values for the R's, but it will define all the values for you. There won't be incomplete values. Because, as I said, you have fewer equations than variables. So the question is, what can we assume that the organism wants to do? And the simple answer, it wants to survive at any cost. So such an assumption might be maximize the energy reserves or maximize the biomass or the rate of biomass. So if you do assume this, then this submodel here is closed. It will give you an answer, which then you can feed to your process optimization problem. The process optimization problem is that I want to maximize the production of a metabolite. I don't care what the organism wants to do. I want to maximize what my process is doing. So you have two things. An objective we've ascribed to the process itself because it's an organism, and an objective on top of it, which is the engineering objective of the design of the process. So the bilevel programming problem, BLP, is an optimization problem where one of the constraints is itself an optimization problem. It's nested. So we can have multi-levels. If you start like this, you can think for any number of levels, but BLPs are more typical. They appear in many applications, surprisingly, in chemical engineering. And we are looking, let's say, at some applications of this and solution techniques with some of my students, former and current. And so this is what they look like. You have two sets of variables. This should have been only X here. So the upper level is the engineering level, let's say. You want to manipulate X's to maximize a function which depends on x and y, subject to the engineering level constraints, and also subject to the lower level minimization, which only manipulates variables y, subject to its own hidden constraints. So it's the organism optimizing its life, survival, whatever, and it's us trying to manipulate the organism despite its manipulation to overproduce what we want. And that's a bilevel optimization problem. I think this would be a good point to break. You can see that the optimal control problems can be also part of a bilevel problem, because the inner problem could be an optimal control problem. But you're going to see that these typical formulations allow you to build all the necessary, they're the necessary building blocks for generalized optimization problems. And there's like 5 or 6 such subtopics we're going to see. So shall we continue then Friday? Thank you.